This conference will now be recorded.
Okay, good morning, everyone. Welcome to today's seminar on time in the power industry, how and why we use it. My name is Ron Quaid, and I chair the North Jersey chapter of the Power and Energy Society. Also with me is Ken Oxley, and Ken chairs the North Jersey chapter of the Industry Application Society. And together we host these joint sessions. I also wanted to recognize that Gary Smolin is joining us today. Gary chairs the Lehigh Valley chapter of the PES. Couple of logistics about today's seminar. I'm going to keep everyone muted. If you do have questions, if you can, please type them into the chat, and I'll try to interrupt Bill. I think Bill will be also monitoring the chat, and we'll answer the questions as they come up. It also gives me a chance to capture any questions and make sure we've addressed them all at the end. The slides for today's presentation will be shared in a OneDrive folder. I'm going to put the link to that folder in the chat session shortly. Also, the recording of this session will be loaded to that OneDrive folder as well. It probably takes a couple of hours to compile the recording. I'll load that up later today. Couple of comments, as you may have just heard Ken mention. We honor outstanding engineers in our section every year. Herman Zablotsky, who's joining us today, was our most recent one. But we also have the ability to honor what we call junior engineers. So if anyone has a nomination for a junior engineer, that's someone with less than 15 years of experience, if you can send me some information about them, I'd be happy to look into nominating. So today we'll be issuing 0.2 CEUs, continuing education unit credits, or 2 PDHs, professional development hours. Payment for this course, as well as the CEUs, is being provided as a courtesy of our North Jersey section. Will remain virtual during the pandemic. I'll also load the link to the evaluation form in the chat shortly. So on to the topic at hand. Today's presenter will be Bill Dickerson of Arbiter Systems. A little bit about Arbiter. Arbiter Systems Incorporated manufactures GPS-based precision time clocks, synchronized power measurement and power calibration products designed to support industries where precision timing is mission critical. Applications include synchrophaser measurements, synchronized power measurements, computer network time synchronization, event timing, and other electric utility support. These products enable the power distribution industry to deliver safe, reliable, and economical power to end users globally. Designed, assembled, and serviced by Arbiter, these solutions provide the backbone for professional monitoring, measurement, and analysis of power systems performance. Bill, give me 1 second because I'm going to mute everyone, then I'm going to have to look for you in the list and unmute you, so give me a second. But with that introduction, I wanted to thank Arbiter for agreeing to present today. And without further ado, I'd like to turn it over to Bill Dickerson to get us started. 1 second. The problem that I have is there's so many folks on the list, I got to go searching for you, Bill, so bear with me. Okay. Bill, I think you might have to unmute yourself.
There we go.
Okay, thank you very much. All yours.
All right, well, thank you, Ron, for hosting this and organizing it. And happy Good Friday and Holy Week to everybody. Thank you for being able to take the time to join us. Today, we're going to talk about time in the power industry, how and why we use it. It's something that Arbiter has been involved with even before the GPS days. We had clocks back in the 1970s that ran off the old GOES weather satellite system that broadcast a time code for the purpose of synchronizing remote weather gathering stations. It was kind of a time division multiplexing thing. So we've been at this for a while. See if I can get this thing to work. There we go. So this is what we're going to be talking about today. First, a brief introduction, applications, requirements for accuracy, depending on what kind of applications you're doing. We have lots of issues with the time industry, with time scales and time zones, leap seconds, that kind of thing. Talk about how those impact what we do. Describe the common sources for precise time and how we distribute that time in a substation or elsewhere. And then spend some time on talking about problems that can be encountered in using precise time in the power industry. So here are some of the applications that we see time being used for. Event reconstruction in the event of a fault. Time tagged records are very, very helpful. Matter of fact, essential in figuring out the sequence of events and what happened. Synchrophasers, people are getting to be quite familiar with these. Basically very precise power measurement that allows us to monitor the system from a wide area perspective. Measuring system time and frequency deviation. The 60 hertz power grid signal in North America and many other places is used as a time reference to run wall clocks and things like that. So the utilities use precise time to keep the frequency, the average frequency adjusted for that purpose. Multi-rate billing, you're probably familiar with the fact that utilities charge different rates at different times of the day. There are power quality incentives, the same sort of thing, that it's important in different times of the day. There are greater concerns and issues than others. General time tagging of recorded data. Remedial action, wide area measurement schemes. These are things that allow the system to be protected instead of, most protection operates to protect a single asset, a generator or a transmission line or something like that. Remedial action schemes based on wide area measurement systems are used to protect the overall operation of the system itself by doing something that you wouldn't necessarily suspect necessary on the basis of a single asset. Traveling wave fault detection used to locate precisely locate a fault, generally to within a couple of towers, to assist with dispatching repair crews. And end-to-end relay testing, when you're actually testing relays on both ends of the line, you need to be able to generate some sort of synchronization between the test sets at the two ends. So it's just a few applications. Talk a little bit more about each one. Event reconstruction is what's been one of the earliest applications actually of time in the substation. This was most of what the GOES clocks were used for, was event reconstruction, because they were capable of giving roughly a millisecond time resolution, which is adequate. It's a small fraction of a cycle. And so what we will do is take a whole bunch of recordings at different locations, and when a fault happens, you can go back and collate that information into temporal order and see if you can figure out what happened first, what started the fault. And excuse me, the industry has found that the old way of doing it with unsynchronized recordings and chart recorder strips on the floor in the substation after a fault was possible, but quite difficult to put into order based on the artifacts in the recordings. So having time stamped accurate information is very useful in the event of trying to reconstruct a fault. Synchrophasers you're probably becoming familiar with or heard of at least. They're basically measurements of AC quantities on the power system, and they're synchronized in time so that basically every PMU that's out there is running on the same time scale, and their sampling is even synchronized to each other in effect. And we express those as phasers. And the PMU, what it does is measure as absolute phase angle. It measures the phase angle at the location of the measurement relative to a standard cosine wave that's synchronized to the top of second. And that isn't all that useful in and of itself, but what it's useful for is by looking at the difference between two PMUs measurements, and that gives the relative phase between the substations or the feeders or whatever, as long as the PMUs have a common time reference. So that's why we use the precision time for PMUs. And there are other things we can do. Measuring power flows and frequency is a very important application actually of synchrophasers, because frequency instabilities tell us a lot about what's going on in the grid and whether or not some mode has become marginally stable. And so that information is made possible by use of synchronized data coming from a bunch of different applications in the grid. Mention a bit about system time and frequency deviation, because the line frequency is used as a time standard, and system frequency varies as you know, the utilities operate the system. But when the power grid is under less stress and lower loading situation at night, it's possible to change the generator rate slightly to get rid of the accumulated error. More and more people are not that interested in worrying about the system frequency, because everybody's got computers that are connected to the internet where you can get NTP. But my understanding is many utilities are still keeping their 60 hertz and 50 hertz signal synchronized, because there are still applications that require it. And this is, as I mentioned earlier, one of the oldest applications of precise time. Multi-rate billing, power quality incentives. There's incentives to companies to use off-peak power, and they get lower rates for that. So when you do that, the billing, the energy meters have to be synchronized in order to know what time it is. And very often that's done with a clock in the substation or near the customer's site where the meter is, that's synchronized with IRIG or SNTP or something like that. And the differences in rates for these large customers can be significant, so the amounts of money you're talking about are considerable, and it's important to keep the time accurate. And sometimes the utility will have a meter on a line and the customer will have its own meter, and when you get disagreements, you get disputes. So if the meters aren't synchronized, then you won't get the same answer. So having accurate time is an enabling technology for multi-rate billing and power quality incentives. A number of standards require time tagging data. You're probably familiar with IEEE 61850 and ComTrade. They provide fields for putting the time tags in the data stream, but most of them don't specify accuracy or even what time scale you're using. And that can result in measurements coming from different places that are incompatible. And excuse me. It's important that the time tags that are recorded have to match when something actually happened. And this comment about PSRC Working Group H3 finally finished their work a few years ago and has standard PC 37.237 was published that specifies how to guarantee that the accuracy of the different time tags on different devices match up. Remedial action schemes and wide area measurement, as I mentioned, they use PMUs for that, and as opposed to looking at things on a asset by asset operation basis, it provides a big picture view of the whole power system, and it allows the utility to identify problems, typically potential instabilities due to some combination of assets being down for maintenance or because of a fault. And if the system is getting to the point where the stress levels are running the risk of taking the system down, system-wide protection actions could be taken by selective load shedding or turning on a backup generator or whatever to avoid large-scale cascading failures. And almost every large-scale cascading failure that's happened in the last few decades goes back to a fairly unique situation of certain assets being off and something happening here, and they often take hours to build up to the point of a cascading failure. And with synchronized measurements of all of the different things going on in the grid, we're able to see what's happening. And since these things do take hours to build up to the point of a failure, that gives the operators time to take remedial action to avoid it. Traveling wave fault detection. Well, you know that transmission faults not only happen in remote locations, they always happen in the most inconvenient remote location, expensive to get to, flying out a crew on a helicopter or whatever. So knowing where the fault is greatly minimizes the cost and time to remediate that failure. And what happens when there's a fault is that when lightning hits the line or the line hits a tree or whatever, the high frequency signals are imposed on the line due to those currents. And that can be detected at the end of the line by looking at the current artifacts traveling back on the line. And that event signature propagates at whatever the propagation velocity is on that line. It's usually nearly the speed of light because the dielectric is mainly air. So if you can measure the difference in arrival time at the ends of the line, you can calculate the fault location that matches up to that. And this is an application that requires very precise time because the speed of light, basically 1 nanosecond per foot. So if you want to know within 500 feet where the fault is, you have to be synchronized within 500 nanoseconds between the two ends of the line. You have, in the event of many transmission line protection schemes, the protection is coordinated between the two ends of the line. They usually have data communications between them. And if you want to validate that with relay test sets, you need 2 relay test sets to generate the appropriate signals at the ends of the line. But the test sets have to be synchronized. So when you generate a simulated event to verify the relay, they both have to do the same thing at the same time. So it's another application that accurate time makes possible. So we're going to talk a little bit about the accuracy requirements for these different types of application. And you see the list of them there. We'll go right through it. For event reconstruction with recorded data, the data is most useful if it's recorded in a small fraction of a cycle, with accuracy of a fraction of a cycle. And there's the lengths of power line cycles of 50 and 60 hertz. A quarter of a cycle is 4 or 5 milliseconds. And their standard PRC 018 requires 1 millisecond accuracy. That's of the clock in the IED that's doing the recording. And if there's 1 millisecond accuracy between all the devices, then they'll overall be accurate within 2 milliseconds of each other, which is about 1/8 of a cycle. And that's generally considered to be good enough for most applications. Phaser measurements require a bit better time accuracy, because under C37118 and IEEE IEC 60255 118.1, maximum total vector error specification is about 1%, which requires 26 microsecond time. It actually requires better than that, because you don't want to allocate all of the error budget just to time offsets. So if you allow 20% of that, that gets you down in the single-digit microsecond requirement. And of course, GNSS synchronized clocks can easily meet that. And there's other things in the substation that typically add much more in the way of phase and magnitude errors, especially CTs and PTs used for relaying, that they have a very high dynamic range, but the normal operating current is way down on the magnetization curve, so that the phase offset tends to be larger than it would be at higher currents. So typically, we can get down to a fraction of a microsecond, which is great, but data is still usable up to as much as 50 microseconds, because that gives you about a 1 degree error, and that's not ideal, but it's still usable. For system time and frequency, what we're interested in is really the time offsets between the different locations and the grid. And generally the utilities will try and stay within at midnight, or whenever they hit or start doing their adjustments till 6 in the morning, they'll try and get down to a few milliseconds offset to start each day more or less on time. And it doesn't stay that accurate over the day with the operation of the power system, but as long as on average it's brought back by 6 in the morning or whatever their target time is, they're okay. And that requires a few milliseconds. That, as I said, is one of the original applications for the GOES time clocks. For billing and power quality incentives, basic accuracy, a fraction of a second is probably okay. But for power quality incentives, in order to look at the actual effects on the waveform that are being imposed by a customer's load, it needs to be more accurate than that, in order to make sure that the harmonic and other information agrees between the customer and the utility. And traveling wave fault locations, I mentioned, basically 1 nanosecond per foot, roughly. And so the more accurate the time is, the more accurately you'll know where the fault was. And 100 nanoseconds, which is equivalent to 100 feet difference, which will get you down to about 50 feet error on the fault location, is practical with today's technology. And so that makes traveling wave fault location a practical thing to do. And it's, as we said earlier, very useful to be able to know where to send the crew out to fix a line that's down or whatever's happened. And then relay testing. Generally, a millisecond is accurate, or adequate. It's a similar kind of thing to the fault recording scenario. And accuracy is typically can be made much better. It can be made easily 1,000 times better as far as the synchronization signal that's available to the relay tester. So again, certainly possible with today's technology. One of the things you get into when you start learning about using time is the fact that we've got all these different time scales and leap seconds and other issues, daylight savings jumps. And that can cause problems if one utility is on a different time than another and they're trying to exchange event records, let's say, after a fault. And the most obvious thing is if one's in the Eastern time zone and the neighboring one is in the Central time zone, you're going to be an hour off. And the other thing is when daylight savings time changes or when a leap second happens, there's often a period of time where there's some uncertainty between all the different IEDs and different locations, taking different amounts of time to adjust to the changeover can result in lots of problems with keeping things synchronized. So we've got different time scales in the world. You've probably heard of UTC. Some people used to call it Greenwich time, which is the basis of civil time worldwide. TAI is International Atomic Time, that's maintained by a bunch of member laboratories of BIPM all around the world, including here in the US and everywhere else pretty much. They have a whole suite of atomic clocks that they average together to give International Atomic Time, and that's what they call it, the ideal atomic time. Now, the problem is they want to keep time, the astronomers especially want to keep time adjusted to the Earth's rotation so that noon really happens at high noon. And the Earth's rotation, however, is a little bit slower than the ideal time is running. So what UTC is TAI adjusted to approximate solar time. And right now, TAI is different from UTC by 37 seconds, and that changes. I had to change this slide before this presentation because the time that I wrote this and gave this presentation last, it was a few seconds different than that. Loran time is not used as much anymore, but it's another version of time that started at it uses TII without any leap seconds in it, but it started when there was 10 leap seconds accumulated. GPS time is the same thing, started in January 1980. At that time, there were 19 leap seconds accumulated. So the UTC TAI difference changes as leap seconds happen, but the Loran and GPS time don't. And that has a lot of advantages because when a leap second happens, things have a possibility of being out of agreement in different places. You heard of GMT. A lot of people still use the term, but it's actually obsolete. It was replaced by UTC in 1972. But you still hear that GMT is used for either the UTC time scale or Western European Standard or Winter Time. But since the term is obsolete, it's really not the right term to use. Local time is another issue that is a problem between different utilities in different regions. Some utilities are large enough to actually span different time zones within their own service area. Others don't, but they coordinate with other utilities that are in different time zones when doing fault analysis. And it's based on UTC, with almost all places, but not all, are an integer number of hours different. In the Pacific time zone where Arbiter's factory is located is -8 hours from UTC, which means it's 8 hours earlier in London than it is in California. And that's in the winter. In the summer, it's 7 hours difference. So it's not always the same. And that's another problem. But there are some locations that use half-hour, even 15-minute increments. And for example, in Newfoundland and Canada is, I think, 3.5 hours different from UTC. And so that provides even more challenges. Clocks have the ability to be set to those local time zones, but we really don't recommend using local time for most applications because of the differences. Daylight savings, or summertime it's called in some parts of the world, is normally a 1 hour advance in time. And it's intended to give people more time to do things after they get home from work. But it ends up causing a lot of trouble, and there's always recurring efforts. There's another one going on right now to try and get rid of daylight savings time. The state of Arizona doesn't observe it, and here in Utah, where I live, they're trying to get rid of it here because it's an inconvenience, and they really don't see any advantage to it. So we'll see what happens if that is. But that's all legislative, and that's one of the problems with local time zones, time offsets, summertime schedule. All that stuff is creations of legislation generated by people in Congress or wherever. And so it's subject to change. And some years back now, the US changed the time schedule for when daylight savings time comes on and off. Most provinces of Canada wanted to be synchronized with the US, so they had to change, even though they didn't really want to. Some states don't observe it at all, and some areas are in different time zones in the winter, and the summer is a small area in British Columbia that's right on the gap, or the border between the Pacific and Mountain time zones, and they just don't change their clocks. So they're in sync with the Pacific time zone in the winter and the Mountain time zone in the summer. And you have to be prepared to deal with that when you're traveling around in that area where I used to live. And so you always have to be ready to adjust your clock or potentially miss your flight if you show up the day of the daylight savings time change, which is on a Sunday. If you're flying somewhere and the plane's leaving an hour earlier and you don't get there, you're gonna miss your flight. As mentioned before, leap seconds are used to adjust the difference between TAI, which is a monotonic time scale based on atomic clocks, and UTC, coordinated universal time, to keep UTC time approximately the same as solar time. And they try and keep it within 1 second. This is a 1 second resolution of the basic time scale. And as the Earth's revolution slows, which it's running a little bit slower than TAI and has been for a while, every so often an extra second is added to bring things back into alignment. The standard allows for negative leap seconds if the Earth speeds up, but that doesn't happen very often. Actually, the Earth's rotation speed does increase a little bit every now and then, typically when there's an earthquake. And that the interesting thing is how that happens is the earthquakes generally happen in a way that causes mass to drop toward the center of the Earth. And that, just like a ballet dancer, when she pulls in her arms and legs, she can spin faster. And the same thing happens with the Earth's rotation whenever there's a large earthquake. Causes the angular rotation speed of the Earth to slightly increase, but it's already running a little bit slower than UTC, and so it doesn't increase in speed enough to actually cause a negative leap second. They're allowed in the leap second standard, but in history, as far as I'm aware, they've never happened, and they're not likely to happen unless we have a really big earthquake somewhere along the line. So probably cause other problems than that. Leap seconds are always introduced at midnight UTC time scale at the end of a month, typically June and December. It can also happen in any month really, but all of the recent history has been June and December. But the thing to remember though is that's not midnight local time. It'll be at 4 or 5 o'clock in California in the afternoon, because California is either 7 or 8 hours different. And so, you think, well, if it happens at midnight, you might not notice it, but if it happens in the middle of your workday, and you might notice it. Particularly if you're doing something that depends on having time accurately, like doing fault reconstruction. This is an example of what a leap second looks like. And you can see the actual added second there is in yellow in the middle. And what you have is a second where the second's value is 60. In other words, normally it goes 58, 59, 0, 1. Well, when there's a leap second, there's an extra second, and it's given the second value of 60. And a lot of systems don't accept that as a valid time. They say, well, the seconds can't be any higher than 59, so it'll reject it, say it's an error. Or in the case of binary time scales, what you see is a little bit different. You get 2 seconds in a row that have the same time, 57,600 in this particular case. And when the system receives 2 seconds in a row where the seconds are the same, then sometimes it says that's an error, because it's not expected. Time's expected to advance monotonically from 1 second to the next. So anything different than that will be detected and sometimes flagged as an error. At the least, a lot of systems have what they call an error bypass, so that when the time changes, it looks for excuse me, a consistent time change that lasts for several seconds. So the purpose of that is to ignore a transient error. What that'll mean if that happens and a leap second occurs is it'll be 3 or 4 seconds after the top of the hour when the clock and the IED finally says, well, I guess the time really did change. And that's where the problems with leap seconds come from. And when I wrote this, which was quite a few years ago originally, there was a discussion going on to getting rid of leap seconds, and that's still happening. There's still a discussion. The astronomers think that they own all the rights to time because the observatories used to be the ones who kept time back before there was atomic clocks. Telecom, airlines, the tech industry, most other network-based industries are in favor of getting rid of leap seconds. And the results of this effort are still not known because so far every time it comes up, the astronomers oppose it, and other people don't speak loudly enough to overcome that objection. And so we don't know if and when they'll ever get rid of leap seconds. They've talked about replacing it with a leap hour every few centuries, or however often it would have to be, and leap minutes and other things, or just letting the Earth's rotation slowly drift out of alignment, but no decisions have been made on that. Coordinating time across some kind of a network. Do things humans have done change the speed of rotation? Damming of rivers. I would guess they probably do. They have some effect. Whether it's measurable and significant, I don't know. But there are, if you look at the rate of rotation of the Earth, it's varying all the time. And you know, even things like water evaporating and going up higher into the atmosphere will cause the moment of inertia to change in a way that will change the angular rate of rotation. So I would believe man's activities will have some effect. You know, launching satellites up into the sky 12,000 miles up, you have a 5,000-pound satellite up there. That that thing is now not part of the Earth, but it's having an effect on the Earth. So yeah, all that stuff I would think would have an effect. Probably not large enough to be terribly noticeable, but it does. Has to have some effect. The problem with coordinating time across any kind of a network, including the power grid, is all these local time zones and summertime changes and legislative changes causing it to be different. And those cause problems. And NERC and the utilities and the regulators have noticed this. And so now NERC requires utilities to store and transmit data using UTC. Now, that doesn't mean you can't have local time on your clocks in the substation or in your control centers. You certainly can. Most of your employees that are going out to work on the equipment will be operating on local time. And we endorse the NERC recommendation to use UTC for all internal data transmission. That means that information can be exchanged between multiple utilities on a common time frame. But there's no problem with using local time for display purposes. And you can set your substation clocks to generate the UTC time tags and UTC IRIG signals for the for your IEDs and so forth, and then have a local time feed on, say, a serial RS-232 port that drives a display. They have that kind of capability, so it's certainly feasible to do that. And you can also apply the local time correction in an IED, the information in the IRIG time streams and PTP and other ways of getting the time out have that those local offset numbers in them now. Where does precise time come from? Well, these days, almost all precise time that people are using is coming from global navigation satellite systems. GPS, of course, is the first of those. The Russian GLONASS system came shortly thereafter. Galileo, run by the European Union, BeiDou system run by China. And there are also regional systems. IRNSS is a system in India that provides time in the Indian subcontinent and a good part of the Indian Ocean. There are also standard radio transmissions. WWVB in North America is used, and microwave and terrestrial distribution has been used, and the atomic standards are sources of precise time. Global navigation satellite systems consist of a worldwide network of satellites that broadcast precise time and position data. And when you have data from at least 4 satellites, you can receive what they call pseudo-range data from the satellites and solve that with a set of simultaneous equations to give you your position in 3-dimensional space and the time. Accuracy is typically 50 meters in 100 nanoseconds. Actually, it's gotten better than that as time goes on, especially now that we have multiple systems up there and you can average the results together. But for purposes of timekeeping, once you know where you are, once you know your position, X, Y, and Z, you can solve with one satellite to find the accurate time. GPS is still the most dominant system in the world, although countries that have their own are trying to force people in those countries to use the local system. Well, it's getting so more and more receivers these days accept multiple systems. And most of our clocks now will receive all of the common worldwide GNSS systems. GPS originally was developed by the U.S. Department of Defense, the Air Force. It was initially operational in 1980, partial operation. Will Elon Musk's Starlink be used for timing? I don't know. It is possible to use low Earth orbit satellites to provide precise time. They just have done some, the Department of Homeland Security has recently done some evaluation of potential backups to GPS, and at least one of those was based on low Earth orbiting satellites. And it is certainly capable of doing that kind of thing. Whether that'll become commonly used or not, it's hard to say. The problem with GPS is it's so ubiquitous and so inexpensive. You know, these days, pretty much every little bit of electronic equipment that has the possibility of having an antenna has a GPS receiver in it that can give you time and position. And the signals are free to use. Most of these low Earth orbiting satellite systems are fee-based services. And so, you know, people have to have a strong incentive to want to use that. Excuse me. The GPS system, though, and all the other systems, their basic services are free to all users. In the case of the US system, there's military signals that are free if you're in the military, but they're not even available to the civilians. Capable of providing time accuracy of around 10 nanoseconds. There's 24 plus satellites. What that means is there's 24 in the standard constellation, but there are spares that are called on-orbit spares that are actually up there operating and providing additional information, so you get more satellites in view. That provides a little bit better accuracy. And cost of the GPS system, as it is with the others, is being paid by the United States government, which is why it's free. That's kind of what the satellite constellation looks like. The satellites operate in 6 different orbital planes with nominally 4 satellites in each plane. And ones where there's extras, they'll have 5 on a particular plane instead of 4. And as I say, provides increased visibility. And that's increased visibility is useful if you're in a deep canyon location or somewhere else where you can't see the whole sky. The GLONASS system is a Russian system, similar in many ways to GPS. The little technology differences are there. Accuracy is the same or a little bit better than GPS. It's a little bit higher power transmitters, which gives better signal to noise ratio. Originally developed by the Soviets in competition with the US military, and then after the breakup of the Soviet Union, they had other things to worry about, so the system degraded and they lost a lot of the satellites and didn't have the resources or didn't choose to replace them. But the Russian government has now since built the system back up and restored its operational capability. And there's a signal that is, I believe, now available on a few satellites, the L1CR signal, which is compatible and on the same frequency band as GPS and Galileo. And last I had heard, most of the GLONASS receivers still use the signal up at about 1600 megahertz instead of the one at 1575. But eventually all of the systems in the world are going to have signals on the same 1575.42 megahertz frequency that GPS and Galileo use. So they can all be received with a single receiver on a single channel at the same time simultaneously. All of these additional systems that I talked about run on the same basis, same basic operational principles, GPS and GLONASS. BIDOW and Galileo are fully operational and available. The Compass system, the BIDOW system, originally was like the IRNS system in India, was only covering the area around China, but they have now their geosynchronous satellites up that provide worldwide service. And the Indian system still has capability for, as I mentioned, the area around the Indian subcontinent and the Indian Ocean. Most new receivers will receive all or most of these different systems. Another source of time is from standard radio transmissions. These are generally in the low frequency band. between 50 and 100 kilohertz typically. There are also high frequency signals that are available, but because they bounce off the ionosphere, the path delays have a lot more variation, and so their time resolution isn't as accurate. Whereas WWVB and DCF, for instance, operate in the low frequency band that has the potential of providing around a millisecond accuracy, which is good enough for some applications. But one of the big problems with these signals, as I mentioned, the high frequency signals are subject to serious ionospheric variations. But the VLF signals, like the WWVB and DCF, are also subject to interference from corona near high voltage equipment. That makes it limited, the amount of usefulness that the system has for power applications. Some utilities have used their internal communications system. Bonneville Power Administration for a long time maintained a microwave link to distribute an IRIG-B modulated time code between their substations. They had this microwave link to provide data links anyway, so they just assigned an audio channel of distributing this IRIG signal, but it's an expensive way to do it compared to GPS, which the signals are free and the receivers have gotten to be, not very expensive. So most of the utilities that were doing that kind of thing have changed over to GNSS-based timing applications. Atomic standards are also usable. Cesium beam standards, which is what almost all of the members of the international timing community use, HP 5071, and which I guess is now made by Symmetricom, which is a division of Microchip, was Microsemi, now Microchip. These things are very accurate, but they're also expensive, and every 5 to 7 years you have to put a new cesium beam tube in the thing, and those cost almost as much as a standard. That's the expensive part of it. So you're looking at several $1,000s a year to budget just to replace the cesium beam tube every so often. But they can maintain their accuracy for a long time, for many years, and they're a fundamental standard, which means that basically just they depend on a resonance and an atom that is known to an very accurate level, and if the thing is operating, it's generating the exact correct frequency. It's dictated by quantum mechanical numbers that don't change, at least that don't change in the time scale that we're aware of. Turns out the rate of time is actually changing at like a part in 10 to the 17th per year. And they've now developed atomic clocks that I saw one of when we were in France at the French timekeeping lab there, and we had a IEEE 1588 meeting. They have a laser-based optical clock that is capable of providing stability on the order of 10 to the 17th, and it allowed them to validate Einstein's prediction and through the theory of general relativity that time actually changes. The rate of time is changing. It's just changing slowly enough that until this super accurate atomic clock came along, we weren't able to validate and verify that. But very few people are using cesium beam standards for operational purposes. There are people in some of the financial institutions that do trading, and they need to know this sequence of orders that come into the exchanges, and they want to maintain that very accurately. You're talking about a lot of money here, so to them $60,000 isn't a big deal. Most substations and other power grid applications, people don't want to spend that kind of money, and the GPS and GNSS receivers have gotten to be economical and reliable enough that they're the choice of most utilities. Rubidium oscillators are being used now for high accuracy holdover capability in substations, capable of maintaining timing of roughly a microsecond a day in the event of a fault, or fault to the GPS system or an antenna or something else going bad that causes loss of the GNSS time. That adds only about $2,500 to the price of a clock. So if you have a critical substation where you want to make sure that even if you lose GNSS time, you have an accurate backup, that's a viable possibility. Those aren't a fundamental standard like cesium is, but their frequency is quite accurate, and more importantly, they have very good stability. Okay, now we've got this accurate time signal. How do we get it out into the IEDs that need it? And there are a number of different ways of doing this, and I'll talk about each one of them. including 1 PPS, 1 pulse per second is basically electrical signal, IRIG time codes, Interrange Instrumentation Group, military group originally developed that. There's an IEEE extension to that, and we have serial time codes that can be sent over an ASCII link, usually used to synchronize computers and displays and other things that don't require super high accuracy. And then we've got network time synchronization, NTP, SNTP, you've heard of, I'm sure, and PTP or IEEE 1588, and there are some other network time protocols as well. 1 PPS is used by all the international standards laboratories for precise comparison of clocks to BIPM standard time, for instance. And the reason is because it's got an extremely high accuracy, excellent accuracy on time mark. It can be down to a nanosecond, the rise time of the 1 pulse per second, and limited only by care and execution, really. And 100 nanoseconds is routinely achievable. The standards labs that are comparing time to UTC routinely achieve better than 10 nanosecond comparisons using 1 PPS. Problem with 1 PPS is it's good for a frequency measurement, which is what the time labs are interested in, but it doesn't really give you any information above and beyond that. Time of day, for instance. So it's been supplanted by IRIG-B for quite some time now in power systems, because IRIG-B is also a digital system with the same kind of accuracy in the rising edge of the pulse, but it does include the time of year. IRIG time codes. IRIG stands for Interrange Instrumentation Group. It's an agency of, or smaller than an agency, I don't know what they call it, a division or whatever of the US Department of Defense. And they created standard time codes back in the 1960s because every range had its own time signal that they were using. And what they did with these things was they would generate this signal in the audio band of basically a modulation on a 1 kilohertz tone typically, and it could be recorded on an instrumentation tape recorder, along with data coming from transducers when they do a test on a range, you know, a missile shooting down a drone or something like that. They'd have a whole bunch of instrumentation in different locations receiving data coming down from the missile and the drone, and they want everything to be time tagged so they could compare it later when they look to see what happened, if the thing worked or didn't, and what went wrong if it didn't work. So they created this standard set of time codes so that all the ranges could use the same set of time codes, and they could, more importantly, get standard equipment from vendors that since it was a standard, that all the vendors could use the same one, and they didn't have to support a whole variety of different ones for each different range. And once they became standardized, they became used basically universally in the military, including NATO and other applications, as well as in the power industry. And IRIG-B is still commonly used in power systems. At the time I wrote this, 90% of all IEDs were still synchronized using IRIG-B. At this point, there's a larger number that are using SNTP, and some people are using PTP now, but IRIG-B is still kind of the backup timing method if we want simple, reliable time in an IED. And it provides basically a 1 per second time mark like 1 PPS, plus it gives you 100 bits a second of data, which has time of year and some other information on it. This is what IRIG-B signal looks like. It's a 100 bit per second, 10 millisecond frame, and it has a modulation which depends on the width of the pulse. The wide pulse there you see is basically a position or reference bit that's used for framing. The data bit for 1 is 5 milliseconds long or 50% duty cycle, and a 0 or index bit, anything that's not a data or position bit, is broadcast with a short pulse of 2 milliseconds. Most applications in the power industry use the unmodulated or level shift code, and that's basically just a digital binary signal, 0 and 5 volts. Some applications, RTUs, in some cases, still use a modulated code. That has the advantage it can be transmitted over an AC line, like a telephone line. It's basically a 1 kilohertz signal that's amplitude modulated in accordance with the same code that's put on the unmodulated signal. The IRIG code, as I mentioned, is designed to be transmitted over voice grade channels like instrumentation tape recorders and telemetry systems. It's because it's basically a narrow band, low frequency signal. It's very easy to transmit. It terminating the transmission lines that we'll talk about in a little while is not really much of an issue. You can run it over any twisted pair telephone type line. And the IED inputs generally have they would on a modem, will have a transformer isolation. And you can get accuracy of 10 to 100 microseconds. And for some things, that's perfectly good enough. The unmodulated level shift, or TTL format, is much more accurate. It has the same accuracy of 1 pulse per second. And again, IED inputs are generally opto-isolated. They use an opto-isolator or a digital isolator these days to break ground loops and protect the input of the IED from transients. We now have extensions to the IRIG code, which are standardized by the IEEE, because the IRIG codes were originally designed for non-real-time applications. So if they knew the time of day, that was good enough. But for operating in the power system, we need more information. We need to know things like what year it is. We need to know what the time quality is. Are we still locked to the source of time, or has the clock drifted out of time because satellite signal is lost or something like that? We need advance warning of things like local time changes, summertime changeover, and notification of leap seconds. And all that information has been added to the IRIG code, IRIG B code, by using 27 control function bits, which were allocated in the original IRIG standard and left to individual ranges or industries to use as they saw fit. IRIG standard 200 that standardizes the IRIG B and all of the other IRIG time codes actually adopted the 8-bit 2-digit year code that IEEE developed, and IRIG standard 200 as an optional use of 8 of the control bits. This is what they look like, and you can see that there's on the left-hand side there, it's the basic time information in seconds, minutes, hours, days. And in the column 5X there, you see the year information that's been added. And the column 6 and 7 have the extensions that were added by the IEEE 1344 standard, the synchrophaser standard originally. Leap second pending, leap second daylight savings times pending, daylight savings time in effect, and then so forth down. There's a bunch of other information. TQ there is the time quality, LO is the local offset. All that information has been added. The last 2 columns is SBS, which stands for straight binary seconds. That's a number that runs from 0 to 86,399, and it basically encodes the hour, minute, and second of day in a binary form. We also have serial time codes that are basically data that's broadcast typically in ASCII strings over a serial port, RS-232 or 485, typically once a second, and they have often an on-time character that happens as soon after the top of second as the hardware can generate it. With higher baud rates, you can get this down to less than a millisecond with care and generation, and then you also have to be careful in how you decode it. That's, as I mentioned earlier, it's commonly used to synchronize computers and time displays that a millisecond is good enough for. It can also be used to resolve the 1-second ambiguity of 1 PPS. As a matter of fact, when you get a time out of a GPS receiver module, a little chip these days, inside of one of our clocks, it comes out as a 1 PPS signal and a serial time message. And these have been used for IED synchronization, but more and more these days, other methods are being used. This is an example of what a serial ASCII time code looks like. IRIG standardized on IRIG code J, which is a serial time code. IRIG B codes are the sine wave and pulse codes that I showed you earlier. But code J is an ASCII time transmitted over a RS-232 or RS-485. And the start of header character 01 is the on-time character, and then it follows by day, hour, minute, and second, and then a carriage return line feed, and that's repeated every second. Something that's becoming more and more widely used is NTP and SNTP, and I didn't have time to update all the latest RFC numbers in here. I think there's a new RFC for NTP version 4. RFC is a request for comment, and that's basically a standard issued by the Internet Engineering Task Force, who are the people that originally developed the NTP standard. And it's not, it originally comes out as a request for comment when they're asking people working on the standard to comment on it, but eventually it becomes standardized and stable, and they just keep the same name, RFC, as they had all along. So it's kind of a weird name, but that's, you know, it's not called IEEE TF standard 1305, it just keeps the name RFC. And this is used primarily for synchronizing computers and wide area networks. And the accuracy ranges in tens to even hundreds of milliseconds. And there's also, and the reasons that for that accuracy is that the longer the transmission path and the more uncertainty, the harder it is for the system to compensate for it. It does measure round trip delay, but as you know, with the internet, every packet go by a different route. So there's a very good possibility that the packets used to measure the path delay will give a different answer than the packets that are broadcasting the time. SNTP is simple network timing protocol, and it leaves out some of the stuff in NTP that are responsible for the complexity of the NTP protocol. And that's why it's called simple. And it leaves out the clock discipline algorithms. In order for the network to operate reliably with multiple masters and multiple, or I should say, they call them servers and clients in NTP world, and the ability of an intermediary server to receive time from more than one server, the clock disciplining algorithms are quite sophisticated in order to allow it to do that and maintain stability. SNTP leaves all that out, and it's intended for use in things like what they call the roots and leaves of the network, the very highest level master clocks or servers with, for example, a GPS source, or the lowest level client or slave, or like an IED. The basic accuracy is the same because the basic synchronization method, the way of transmitting and receiving things is the same. The difference again with NTP is it is intended for use in intermediate level servers that are interacting with a bunch of different time sources in different places with different delays and servers coming and going and that sort of thing. Performance of the NTP and SNTP in a substation depends on network topology and stability of propagation delays. Wide area networks, the propagation delays are unstable, like I mentioned, but in a substation, the propagation delays can be very consistent. And local area networks with controlled propagation, 10 microseconds is feasible, but that requires very good care in the design of the sending and receiving equipment. SNTP and NTP almost always operate on an interrupt basis, and so you have to have the interrupt generate a time tag as soon as possible after the message is received, and calibrate out sources of error. One thing that NTP is good for is if you have a 1 PPS signal, then the NTP provides accuracy that's good enough to tell you what, when I say resolve the ambiguity, that means tell you what second a day it is. So if you have NTP and 1 PPS, you can get the second of day and also down to the nanosecond if you want. And there were some applications that have used that more and more. They're ones that are doing that have switched either to IRIG-B or to PTP. And this is kind of how you'd go about distributing time if you wanted to use NTP and 1 PPS to resolve or to provide finer resolution. NTP signal goes over the red lines through the network switch to the IEDs, and the 1 PPS is transmitted over a coaxial, typically, transmission line to the IEDs directly. More and more for high accuracy network connections, people are using PTP, which has been under development for a long time. Originally, I think 1995 or something like that. And it provides hardware level time accuracy by using special hardware in all of the devices, including all the switches and routers. Everything along the path has to have hardware time tagging capabilities. What it does is it recognizes a certain point in the message as being a reference point and generates a hardware time tag, much like you get with a 1 PPS or IRIG signal. If you don't implement the hardware, you get an accuracy similar to what you get with SNTP, some tens or hundreds of microseconds at best. PTP is slowly being adopted, but it still hasn't been widely accepted because of the special hardware requirements and the cost of hardware that has that capability. The way it works is by transmitting a sync message, which goes from the master to slave, and the two time tags are taken on that message at the time it's transmitted in the master and the time it's received in the slave. And the difference between those two is the propagation delay in the medium. And in order for the slave clock to be able to calculate its offset, it needs to know the time T2 when the message arrives at the slave, which can measure itself, but it also needs to know the time T1 when the sync message is transmitted. The message that's being transmitted encodes an approximate time, but it doesn't know when it'll finally, leave the portal of the PHY chip in the transmitting end of the master. So that time is measured in the PHY chip generally and read by the master's processor, and then it's transmitted in a follow-up message, which tells what the time value for T1 is. Then the slave clock transmits a message to the master. It's called a delay request message that is used to measure the time delay of the path. The master responds with the delay response, and doing all that math thrown in the box, you can figure out the offset between the master and slave. The delta T or delta tau sub ms there can be determined by adding and subtracting those numbers, and the delay time can also be found. So those two, the delay time and the time difference between the master and slave, can be determined by solving that set of equations there. PTP network is nice because the same data network is used for both timing and data. That's the whole reason for doing it. And the difference is you have to have an IEEE 1588 compatible GPS clock, an IEEE 1588 compatible IED, and an IEEE 1588 compatible switch, often with a boundary clock or even now a transparent clock. Other network time protocols exist. Time protocol, daytime protocol, they're both standardized by RFCs, used to set computer clocks, and they still are used for that, but they're not optimized for the kind of things we do in the power industry. So power industry tends to use NTP, SNTP, PTP, and IREG instead. I believe the current version of NTP is now version 4. I didn't have time to dig into all that and update it. But NTP has been version 4 for a while. There's not huge numbers of technical changes in it, and for the most part, they're compatible, and the software drivers that are updated in computers and other things will use the latest versions. Summary of the difference between NTP and SNTP and PTP. NTP is used in computers synchronized over a wide area network. SNTP can be used as servers and clients and nearby, typically in local area network applications where the devices are close to each other logically, and the path delays therefore are controlled. It's not going out over the wild west world of the internet where packets will take different routes from one to the next. And PTP is used in local area networks also, and if you have the IEEE 1588 compliant hardware, it can provide accuracy much better than a microsecond. There's a high resolution version of PTP you might have heard of called White Rabbit that was developed by CERN in Europe for their atom collider project that they have over there, and they have gotten down to sub-nanosecond accuracy by also using the 1 gigahertz clock that's present in a gigabit Ethernet link, and it's transmitted over fiber, and they're getting down to sub-nanosecond results with that. So it's all very specialized hardware though, and that's how you get better than the 10 microsecond level you can get with SNTP, is by having specialized hardware. Right now, we're going to talk a little bit about problems that people have encountered in applying precise time in the substation, different issues that happen with GNSS systems and so forth. One question people have, if they have a location, for instance, a hydro system that's located at the bottom of a dam down in a gorge, and you don't have a very good view of the sky as well, will we get enough satellites? Back in the old GPS days when there weren't that many satellites up, that could be a serious limitation. Nowadays, we found that even with only GPS satellites, if you turn the thing on and let it run overnight, it'll generally find its position. And once it knows where it is, there's almost always one satellite at least visible. With multiple satellite systems, including Galileo and GLONASS, there's 3 times as many satellites, so the odds are that almost any installation these days will provide precise time without too much trouble. We've had people that have had questions over the years with antenna cable length and system design, especially if you have a long cable and you need to have preamplifiers in the line and all that. There's information provided to help people do that, and manufacturers' literature, and the factories are always willing to help you on that kind of stuff. Large interfering RF signals, typically that you'd find that where the GPS receiver was co-located with RF and microwave equipment. Newer products are much better at that than the old original GPS receivers were. And we offer, and I think most other companies offer, high rejection antennas for areas where they're needed, but less and less, we see less and less of those problems even with standard antennas. Lightning and surge protection is also an issue in some locations. Florida gets a lot of lightning, for instance, and almost all GPS clocks that are installed in areas like that, you have to make sure you provide the type of surge arresters and lightning protection that's required. Our clocks have a fair amount of that built into them. They generally have, the newer ones have gas discharge tube fault surge protection on the antenna line. You still have to provide a solid ground to it. We have a range of accessories available that also can be used for that. And again, if you have issues and questions with that, always you can call factories and be glad to help. Another thing that you have to keep in mind is if you're using a clock to feed signals to DFRs, relays, RTUs, whatever that are being synchronized by the clock, and if they're operating from an uninterrupted power source, the clock should too, because the clock isn't going to work if it doesn't have power. And so we recommend hooking everything up to a substation battery if it's possible. We're going to talk about issues with distributing dedicated timing signals, and then we're going to talk about network time after that. Typically, IRIG unmodulated and 1 PPS signals, they're logic level signals. They basically look the same other than the waveform that's being transmitted, the way it's encoded. They're generally distributed with copper wiring or fiber, but most applications use copper because it's cost effective and you can put multiple loads on one driver. But for 100 nanosecond accuracy, you have to be fairly careful about how you do it. And you have to make sure that the lines are properly terminated. And the best thing is to drive a single load per output. But for millisecond accuracy, like for synchronizing event recording equipment, like relays that are just going to generate fault records, and you only have to meet the NERC PRC 018 requirement, multiple loads can be pretty easily connected. And if the signal can be decoded by the IED, it'll be at least a millisecond accuracy, which is required for recording. But for a synchrophaser device, for instance, we'd recommend hooking up the clock directly to that load directly without intervening other devices on the line. IRIG modulated signals are very easy to connect. They are basically like a telephone audio channel. So any twisted pair signal, twisted pair or coax, any available wire is generally good enough to distribute it. Generally, the loads have a high impedance or bridging input, and the source is usually fairly low impedance, so you can drive hundreds of them. They also have automatic level control on the receiving end so that the signal level isn't very critical. And the delays are small enough on the wiring compared to the achievable accuracy, which is limited by the way it's encoded and of relatively slow slew rates of the 1 kilohertz signal. So the delays aren't really of much consequence. So for modulated IRIG, we recommend using a shielded twisted pair, but you can use pretty much any twisted pair if that's what you have available. Unmodulated for best accuracy, we recommend a properly terminated coax like RG58 or whatever you want to use, driven from the clock all the way to that high accuracy device with a direct connection. If you're looking at something with lower accuracy, like most recording equipment, any reasonable connection that gets the signal there is okay. Termination is not generally used because the termination, lack of termination causes a bunch of ringing and stuff on the transitions. But the less accurate devices generally have a fairly slow opto isolator to bring in the IRIG signal, and they don't even see that stuff. As I mentioned, the unterminated lines have ringing and overshoot. that will affect high performance IEDs. If you're looking at things down to 50 or 100 nanoseconds with a high speed opto isolator or digital isolator, that device will see that noise and bouncing around on the edges of the signal. And so for high performance applications, you need to look at terminating the line one way or another. We'll talk about that in the upcoming slides. For most applications, for recording only, termination usually isn't required. To work properly, termination is usually equal to the line characteristic impedance, which is a matter of the dimensions of the line and the type of dielectric it uses. Coaxial cables will tell you on their jacket usually what impedance it is. Typically 50 ohms, some are 75, and occasionally you'll see 93. 75 is usually used for antenna systems. We use it on our GPS antennas, as a matter of fact, because it has lower loss. That's the reason why it was developed, is for receiving systems for lower loss. 93 ohms is used in some instrumentation applications, but it's not real common. You probably won't see it. Twisted pairs are normally in the range of 80 to 120 ohms, depending again on the geometry and the type of dielectric. And there's two types of termination we're going to get into, both at the source and the load, that can reduce or eliminate ringing and overshoot. Here's some simple schematics showing on the left a source terminated system. This is where the clock itself includes a series resistor equal to the characteristic impedance of the coaxial line, 50 ohms typically. The second one has a load applied at the far end of the transmission line across the IED input, again equal to the characteristic impedance, 50 ohms typically. And then on the far right is called AC termination, which has the resistor also equal to the characteristic impedance in series with the capacitor. We do that to reduce steady state power loss. Source termination requires the lowest power from the clock, but it's only suitable for a single load at the end of the transmission line, or maybe a couple of loads that are right next to each other, because the signal, if you look at it at the clock end or along the line, you'll see that it's distorted. When the voltage transitions up to the rising edge of the signal occurs, you see the first thing is it jumps up to 2.5 volts, or half the signal level, and then once the signal reflects back from the far end of the line, then it goes to the full 5 volts, and it looks like that all along the line, except at the very end where the load is. At that point where the IED is located, the signal will be nice and pretty at the very end. And this also, another issue you might have is that source resistance acts as a voltage divider with the load. The loads are generally high enough impedance, it's not a problem. But if the load is a 50 ohm load and you put a 50 ohm source impedance, it'll give you a very beautiful signal, but it'll only be half the voltage, it'll be 2.5 volts instead of 5. And here is a chart that shows for our Arbiter clocks what the source and resistance and load capabilities are. I'm not going to go into it in too much detail, but you'll see there's a couple general categories here. There's the one on the left category, which is 50 ohm source impedance built into the clock, and that will match a coax cable directly. Then the ones in our 1200, 1201, 1202, and the original 1084 and 1092, 93 series clocks have a 15 ohm source impedance. And what that does is it provides decent enough source impedance for most applications that aren't super critical. And the four on the next three are all what we call high drive outputs. Those have the ability to generate over 100 milliamps of load or 100 milliamps of current to drive multiple loads. But because of the very low impedance on the rising edge, we recommend some sort of termination at the farthest load in order to keep the ringing from causing a problem. The load termination can be used with multiple loads along the line. The problem is that whenever the signal level is high, it's going to be drawing current. If it's a 50 ohm load with a 5 volt source, it'll draw 100 milliamps continuously when the signal level is high. And that's okay with most clocks. They're capable of generating that in the high drive mode. So you can use a high drive clock and you can put a number of different loads along the line, and they'll all see a nice clean signal. They'll have slightly different delays, but they'll see a signal that they can synchronize off of, and that's the important thing. AC load termination, which is the one with the capacitor in series, requires the same peak current, but once the capacitor charges up, it stops drawing current. So that gives a lot lower power dissipation and consumption. And with most timing signals, only have, well, 200 transitions a second for an IRIG-B unmodulated signal. Again, the clock source resistance, if there is some forms of voltage divider with the termination resistance, you have to look at that. So those clocks at a 15 ohm source impedance in the chart there, the 1200, 1201, 1202. If you use a load termination, it's going to cause that voltage to drop to around 4 volts, which is usually okay, but you have to check and make sure it works. And the termination may need to be increased a little bit if you have a lot of IEDs, and the IEDs load the signal. They basically act as a load in parallel with the termination resistance, so you might need a 60 ohm load instead of a 50 ohm load. Termination resistors you normally want to make equal to the line characteristic impedance. If you do that, it's a properly terminated line and there's no reflections off the end, which is where all the ugliness comes from. And the load termination impedance should be increased to compensate if the IED loads more than 10% of what the characteristic impedance is. And the AC termination, the key thing to choose there is to choose a capacitor that gives a time constant that's about 10 or 20 times the electrical length of the line. And what that does is by the time the capacitor charges up, all the ringing is all come to an end. So if you try and make it too much smaller than that, you can reduce the power being consumed, but you'll start to see it pick up some ringing and overshoot. Is it possible to connect multiple IEDs to one clock output? Yes, it is, depending on the application. There's modulated IRIG, you can pretty much hook it up however you want because the slew rate of the signal is quite small compared to the length of the line, so reflections just basically don't happen with the modulated IRIG signal on any kind of topology you're going to ever see in a substation or other power environment. Unmodulated IRIG has fast transmission edges. You need to have terminated lines. If you have a star configuration with each branch properly terminated, you can do that. Remembering that each load with each line that has a 50 ohm load at the end is going to draw 100 milliamps. So if you have 200 milliamp current capability, you can put star configuration with two loads. And a load terminated line, you can have high impedance select loads anywhere along the line. What you don't want to have is a bunch of stubs hanging off the transmission line. You'd rather bring it from point to point to point because stubs cause reflections that basically can get pretty ugly fairly quickly. The loads, if you have a source terminated line, you should only have IEDs at the far end of it because, as I mentioned, along the line, the signal is distorted. Other digital signals, programmable pulse, 1,000 pulses a second, IRIG modified Manchester code, use the same requirements as IRIG unmodulated and 1 PPS because the critical characteristics of those signals are similar. They all have rise times on the order of 10 or 20 nanoseconds coming out of a clock. And the ringing and overshoot are determined by the step response of the system. And by the time the next signal transition happens on all of those signals, all of that will have died out anyway because the electrical length of the cable is generally much shorter than the time between the signal transitions. The fastest one of those is the 1 kPPS and IRIG modified Manchester, which has a 500 microsecond dwell time, if you want to call it that. And that's a fairly long cable. You aren't going to find a cable like that in a typical power installation. We get questions from time to time about grounding. As with most signals that you're trying to transmit accurately, you need to have the signal grounded at only one location, normally at the source. Most IEDs should have, and most do have, galvanically isolated inputs using an opto-isolator or a digital isolator. You can build floating outputs, and we've done that, but they have to have an isolated power supply, so they cost a lot more than a output that clock that's grounded at that point. So the best industry practice is to ground the time code signals at the source, use IEDs with galvanically isolated inputs, which can be a transformer in the case of a IRIG modulated signal or opto-isolator or digital isolator in the case of a digital signal, one PPS or IRIG-B. And we use single point grounding at the source to eliminate ground loops and provide a safety ground. Fiber optic distribution is something else that we see people use. It's immune to electromagnetic interference, which is actually a very nice feature in a substation or other power system. The expense, though, is normally not justified. It depends on the application. Sometimes for longer distance, it makes sense. And the reason that you generally don't need to use fiber optics is the IEDs already provide galvanic isolation at their input. And the time code signals are highly redundant. And what that means is if a transient happens and it affects one of the bits on an IRIG signal, the IED will recognize that as being using that error bypass I talked about before. It won't follow it, it'll reject it because it looks for a consistent time change for 3 to 5 seconds before it'll accept it. So a momentary interruption of a signal doesn't really have much effect. That's one of the nice things about time code signals is they're highly redundant. We know that the time advances 1 second for each second. When something else than that happens, we're highly suspicious of it. Sometimes longer distance fiber connections are practical. It's often better to add another GNSS clock though, because it's often less expensive than a long fiber connection. But if you're sending time somewhere where a clock isn't feasible, like you have nowhere to put an antenna, then we have people using fiber connections to do that. Delays in distribution wiring. Signals do propagate at nearly the speed of light. In coax, it's maybe 70% of the speed of light. Twisted pairs is closer to 85 or so. Fiber is typically about 70%. And that's generally not an issue when you're synchronizing a recording device that has to be 1 millisecond accurate. The delays are 1 to 1.5 nanosecond per foot or 3 to 5 nanoseconds per meter. And if you're using a high accuracy application like traveling wave fault location or synchro phasers, and you've got a fairly long cable, then the delays can be significant. And we provide in our clocks, and I think most other companies now do, they have the ability to advance the time code that's being transmitted to compensate for the delay in the line. So if you know you have a 100-foot line and it's got 130 nanoseconds of delay, you can advance the time code by setting the cable delay number, advance it by 130 nanoseconds so the time code arrives on time at the far end of the line. As I said, that's only really necessary if you're doing something like traveling wave fault detection or synchro phasers or something else you're trying to get the absolute best accuracy. For recording applications, it's generally not needed. Distributing network time signals. Issues here aren't really the cables because those are pretty well standardized, but what happens to the packets that are going out over the network. And we'll talk about things like TCP versus UDP, managed switch use, message traffic priority, and things along those lines. A lot of people think that TCP is transmission control protocol is better than UDP, but most protocols, including NTP and PTP, use UDP. And why is that the case? Well, the reason is because UDP places all the burden of network problems like missing packets to the receiving device and the application layer. In other words, it's a best efforts method of transmission. You send the data packet out and it gets there or it doesn't. And if it doesn't, you don't get that packet, that's too bad, it's gone. TCP has extensive handshaking and places the burden on the sending device and the transport layer to make sure that the packets get there. And the problem with that is, well, we'll get to that in a minute. The IEDs have limited resources in many cases. So placing a burden on the sending device results in problems because TCP favors reliability of the single packets and wants to make sure the packet gets there. UDP favors the reliability of the connection. So when things get stressful in the system, the UDP protocol will lose packets, whereas the TCP will drop the connection. And you can see for a time transmission, losing an occasional packet's not a big deal, but losing a connection is more of a problem. And since these things basically are opened and run forever, if the connection gets lost, you then have to restart the service. So that's not a desirable thing. So occasional packet loss can be dealt with. TCP, however, is useful for something like a file transfer protocol where you want to make sure you get the whole file, and it's not a problem to wait for a resend. In time codes, having to wait for resends on signals causes more problems than just dealing with a lost packet. One important thing to realize in a substation, I think that the IT people who are dealing with substation stuff have gotten better at this over the years, but most power system protection engineers and people are using time codes and like NTP and PTP over a network, kind of treat the infrastructure, the switches and all that like a black box. They turn it on and run away because they don't know what to do with it. And that works okay for enterprise networks, but mission critical real-time applications like power system protection and control, it can be a problem. And switches have a lot of flexibility and features in there to control message priority and provide for guaranteed slices of time for critical data. And that's provided by the internal settings in the switches. I'm not going to get into this in great details. Quite frankly, I'm not really a high-level expert in this, but the IT people generally do know a fair amount about it. And if they understand what you're trying to do, they can help you to optimize the settings of your network to make sure that your time code data and other things get through with the right priority and reliability. The switches offer things like quality of service settings to assign priority to different classes of traffic. Virtual LANs allow you to set up the switch in such a way as a device doesn't even see traffic that's not really intended for it by keeping excess broadcast traffic and multicast information away. There are port configurations that can be implemented to improve security, like there's ways of encrypting data right in the actually in the Mac itself, MacSec, for instance. IGMP, Internet Group something snooping management protocol, I think it is, allows you to eliminate unsolicited multicast packets, which lots of extra packets pounding on an IED can, especially if the IED has limited processing and memory capability, can overload the stack, the protocol stack in the IED. So keeping a bunch of unwanted multicast packets away from the IED is always a good idea. Can also set up filtering to eliminate undesired traffic coming from unrelated devices. Service level agreement traffic management allows you to reserve a certain percentage of the bandwidth for certain kinds of traffic. IEC 61850 goose messages, for instance, is one you might want to do that for. And they also provide things for SNMP and switches, so you can see what's going on, and port mirroring, so you can hook up a computer to a port and see what's going on a particular device in the network. Controlling message traffic priorities allows you to give certain types of traffic higher priority than other types. And this is something that the managed switch can do, and you have to have the right kind of switch to do it. You have to understand what the requirements are before you buy it and make sure that it's set up right. And then most importantly, you have to actually test and verify that it's working under stress conditions. One of the things that we found in network time applications and other applications with synchrophasers and things like that is that what we call ghost problems in networks, things that work fine and all of a sudden act strange, or every so often act strange. It's often caused by unsolicited traffic, and broadcast and multicast is often an offender because there are situations when broadcast packets get sent out and overload IEDs because they don't have the capability of handling a lot more data than what they expect to have to handle. And sometimes these problems will disappear when you move the IED to a different location, put it on a different switch or something like that. And when you have these kind of problems, unsolicited broadcast traffic and just background traffic that's not intended for that IED, but for some reason is ending up there, you can turn on switch filtering to control that. IGMP snooping is one way, and MAC and IP address filtering is another. other network traffic. In other words, things other than just broadcast and multicast stuff. But for instance, during an event, traffic on the network will spike when people are trying to go on and download event records and find out what's going on. And as I say, that's a bad time to find out that your network's not configured properly. So again, the important thing is when you configure the switches and the IT people set it up, you need to actually test it under some simulated stress conditions. And there are simulators and analyzers that are available to do that kind of stuff. This is some background information on the port numbers that are used for different types of traffic. SNTP and NTP use UDP port 123. PTP or IEEE 1588 use 319 and 320. PMUs 4712, 4713, and on our 1133 we have 2 virtual PMUs in there, and the second one uses 4714. PTP, as I've said several times, the specific network requirements are that all of the components on the network that are in the path between the grandmaster and the client have to support hardware aided PTP to get the sub-microsecond timing that the system is capable of. And that includes the grandmaster clock, the IEDs, and all the switches along that path. It is possible to have a subsection of the network that doesn't have hardware aided PTP ports if it's serving less critical applications, like applications that are just doing recording at the 1 millisecond level and you don't need the hardware aided sub-microsecond timing. But that requires careful design by somebody who really knows what they're doing. So it's one of the reasons people still like iRig, actually, is because it just goes from one point to another and there's nothing in there to get involved in it. You never have unsolicited broadcast traffic or anything like that on an iRig signal. Well, that's all I have in the way of slides. If people have questions, I guess Ron is there and can act as a moderator at this point.
Very good, Bill. Thank you. So we had a couple questions that came up that we answered as we went along. So if anyone has any questions, please feel free to type it in the chat, or you can also unmute yourself and ask it live. I actually do have a question, Bill. As far as clocks themselves, do they have like a life expectancy, you know, besides the normal MTBF, but as far as the clock itself, does it degrade over time?
Well, that depends. All electronic stuff has a lifetime. Most of the stuff that we use in our products, the lifetime is quite long. One limiting factor is if you have power supplies that have electrolytic capacitors in it, those things generally wear out after 15 or 20 years. Clocks that have rubidium oscillators in them, rubidium oscillators and like cesium oscillators have a reservoir of the material in their rubidium metal or cesium metal. Eventually that gets used up and wears out. That's why you have to replace the cesium beam tube every 5 to 7 years for $30,000 or $40,000. Right. Rubidium oscillators that we use have about a 20-year lifespan, which is roughly the same as the capacitors in the power supply. And that rubidium clock also has a small, very long life fan in there that also has about a 20-year expected life. So we tell people with our 1206 clock, which has the rubidium oscillator in it, to plan on replacing the oscillator, the power supply, and the fan in about 15 or 20 years.
So I guess I was thinking more along the lines of drift of accuracy. Does the accuracy change over its lifetime? We realize the electronics could fail, but does the timing drift?
No, it shouldn't. And the reason is because it's basically getting its time from the GNSS system, and all sources of uncertainty in the clock itself are corrected out by comparing to the GNSS system on a second-by-second basis. And it's possible, I suppose, that internal delays might change slightly. I don't think that they would ever change enough that you would be able to see them, but even those delays will be corrected out, though, if it does happen by the continuous comparison to the GNSS signal.
Okay, good, thanks. While we're waiting for any additional questions, I just wanted to remind everyone of the CEU evaluation form. I just put the link again in the chat. If you can get that done today, please. This automated process that we use is working quite well, but we're trying to keep these things moving along. So do the evaluation form before noon if you can.
Also want to let everyone know I'm going to be sending this slide set, which is slightly revised, to Ron so that he can put it up on the website. And there is a companion, I don't know, I call it a companion document that I'm going to revise and send him also.
Yeah, thanks. Along those lines as well, go to meeting. I'm recording this. It takes a couple of hours to basically compile the recording. I'll also load up this recording to the website that I put in the chat as soon as it's available. Does anyone have a question? I think I hear someone unmuting themselves, so please feel free to ask your question.
Yeah, Ron, this is Joe Weber.
Hey, Joe. Good morning.
Ron,
Go ahead, Joe.
yeah, I was just wondering, with so much more distributed generation, what are the demands for more accurate and timing? And are you deluged with timing problems with all of the distributed generation that's coming up these days?
Well, I'm not aware of any specific problems that result as from DG, especially, you know, like rooftop systems. Most of those just synchronize to the 60 hertz that's coming down the line. And there's an IEEE standard, what is it, 15 something or other, 1519 or 1522, there's 1547, that's what it is, that specifies the interaction between DG inverters and the power grid. And they don't generally depend on precise timing at that level. And when you're talking about renewable, yeah, thank you. Talking about renewable energy and larger scale stuff, most of those use PTP or GNSS timing internally. And it's part of the design when you buy a system from one of these big companies that provides the large solar or wind installations. They provide a complete set of instrumentation and everything with it. I'm not aware of any specific problems that are happening at the transmission level or anything that are related to DG, however.
I guess that's good news.
It just means there's a lot more demand for good timing applications. Hey, Bill, there was a question that came up a little bit earlier about, you know, human interaction and affecting time. Things like, you know, damming rivers, affecting the speed of rotation of the Earth. Anything else you can add to that?
I don't think it's material for our industry. The changes would be very, very small. And to the extent they happen, it's taken care of by the adjustment of leap seconds, which actually cause us more of a problem. So I suppose you could say, if we do something that slows time down further, like storing a lot of water at a higher elevation in a dam, I mean, that will slow the Earth down, and that will result in an occasional additional leap seconds. So maybe that causes a slight problem, but it's not really a significant thing, I don't think. We've got bigger problems to deal with.
Dean shared an IEEE standard 1547 for those folks that are not familiar with that. That's the DER, or Distributed Energy Resource Interconnection Standard. So thanks for sharing that, Dean. Rod had a question. How is the electrical industry handling the leap second issue? Is there any manual intervention required?
It's not supposed to require manual intervention, but one of the problems with leap seconds is they happen infrequently. And so unless you use some kind of simulator to test it, you don't know whether your equipment is going to function properly. And there have been issues where during a leap second, some of the equipment in a substation misoperates. Usually it'll come back after a period of time. It'll be off by a second for a while is typically what happens. The synchrophaser community, NASP, has, every time there's a leap second, they gather data from all of their participants as to whether they have identified any issues. And it seems like the people that are building PMUs and clocks that feed those have gotten those problems pretty well under control, but there's still issues with some IEDs, you know, that particularly if they have older designs and haven't had their firmware updated, you know, they might have an issue with a leap second.
Hey, Bill, I have a question rather specific to your clock. So, you know, let's say you're using a clock in a substation application. You need to have an antenna outside that sees the satellites or whatever. how many antennas do you have? How do you lock in? What happens if you lose signal? How does the clock keep time, et cetera?
Well, you need one antenna. It connects to the clock with a coax cable, and it just needs to be outside somewhere where it can see a fair amount of the sky. And how should I put this? We find that the largest single source of problems with GNSS installations is antenna system damage due to unrelated maintenance activities. Somebody will be up on the roof working on something else, the air conditioning or whatever, or putting a new coating of tar on the roof, and they'll damage the antenna somehow, break the cable or knock it off its mount. That's the biggest single problem we find. When things like that happen, the clock will start running in holdover mode. Basically, it'll start drifting, and the drift rate depends on the quality of the oscillator that's installed. Our older clocks had just a simple processor type crystal, and they could drift fairly quickly. The new clocks we have all have an ovenized OCXO inside, which provides no worse than a millisecond per day, typically a few hundred microseconds, even less, depending on the stability of the environment. And if you have a rubidium oscillator, it's more like a microsecond per day.
Okay. Good, thanks.
Yep. It's quiet out there, but I see everyone's still listening.
Anyone have any additional questions?
Just saw one about reclosers. Most reclosers these days are shipping with a small clock built into them, from what I understand, and they do have some communications, obviously, and so they can command them to close at a particular point in time, and also use the data, or use the recloser to gather data about the fault that's involved that they can send back, and the clock is used to synchronize that. So we're selling quite a few clocks to people that are manufacturing and installing reclosers, that's for sure.
Good. I'll just make a comment. Upcoming, I always get questions about what I have upcoming. So what I can say is confirmed at this point is April 16th, that's 2 weeks from today. I have a presentation titled Intelligent Substations, and that's going to be presented by Systems with Intelligence. I also have confirmed for May 14th, something called 3D Intelligent Design in Substations, and that's going to be presented by RCMT. So I'll be sending out my email invitations for that shortly, and you can look forward to that. So with that, I'll just say if anyone else has any other questions, we'll entertain them now. Otherwise, I want to say thank you to Bill and Arbiter for presenting today. Great presentation. I know I learned a lot as well.
Thanks for giving me the opportunity. I appreciate the time and everybody's interest. And if there are any other questions that come up along the lines, feel free to send them to my attention.
One more question came up, which is a really good one. What about cybersecurity concerns with clocks?
The cybersecurity concerns with clocks generally relate to the network connection if the clock has one. And most of our older clocks and simpler clocks aren't even connected to the network. And for those, cybersecurity is quite straightforward. You just have to make sure that if you install a firmware upgrade, which in our older clocks is usually a physical ROM installation, you make sure that it's something that comes from the factory and not from some counterfeit source. I'm not aware of ever having seen a counterfeit clock ROM for one of our products. The testing that goes on the network connections is more significant, and that's an ongoing thing. That of course, cybersecurity is a big cat and mouse game.
Yeah.
Threats are always getting more sophisticated, and there are always updates to the NTP stack and other things to update software vulnerabilities that get discovered. NTP is quite a complex protocol, and complex protocols provide more surface for attack by a bad guy. So that is an issue, and we're working on it all the time, as with all of the other folks in the IETF who's developing or maintaining the NTP standards, the other vendor communities and so forth. There's also a US CERT program that's run by the Department of Homeland Security that tracks vulnerabilities and problems that have been identified. And we work closely with them, as I think all of the other IED and clock manufacturers do.
All right, thank you. Okay, with that, I want to say thanks again, Bill. Thanks everyone for attending. Hope everyone has a great weekend, and happy holidays for those that celebrate, and catch you in a couple weeks.
Thank you all.
Thank you.
Thanks, Ron.
Ron, thanks as always.
More than welcome. Thanks for participating. Hey, Dean,
Yeah, that's
how's it going?
good. Our folks enjoy this, so it's and I'm going to shake the tree a little bit. I might have one or two presenters that I might be able to free up for you.
Please do. That'd be great.
So
Awesome.
thanks,
Sure. Thank you. Thanks for sharing it with everybody.
and hopefully you're not like here in Ohio. We had snow the last couple of days.
I saw
That's
snow
bad.
flurries up the window, but not much.
It is still springtime.
All right. I guess I'll end it now. Have a good one, everyone.
Thank you.
All right. Thanks, Bill.